Hi guys, welcome to the series of lectures on applied statistics, and today we shall continue to discuss how to settle arguments based on statistical evidence. However, this time around we shall discuss the so-called non-parametric hypothesis tests. If you're not sure what a statistical hypothesis is and what the parametric hypothesis tests are, consult the previous lectures on these topics. So let's get going. Parametric tests such as the z-test and the t-tests assume knowledge about the distributions from which we draw our samples from. First off, they require that the observations within the sample must be independent and identically distributed. That is, they should be sampled with replacement and come from the same population. Then, if the underlying population is normally distributed or the sample size is large, we have two options. If the variance of the population is known, we apply the z-test, which assumes a z distribution. However, if the variance is not known, then we apply the t-test. However, if the sample size is small and the population is not normal, then what do we do? So first thing we can try is we can test if the population distribution is indeed normal. For that, we can try a variety of tests, such as a few listed on this slide. You can investigate their individual details yourself, but for each of them, the null hypothesis is that data comes from a normal distribution, whereas the alternative hypothesis says otherwise. Now, null is rejected, then what do we do? Because we can't use the parametric tests for our sample data in that case. Another problem is that these tests have low power to reject the null. That means that these tests may fail to reject the null hypothesis in many cases when they should. So in that case, we can erroneously assume a normal distribution and apply parametric tests. An alternative to these tests is to simply plot the data and use other published information about the underlying population to determine if the data comes from a normal distribution or not. In many cases, it is clear that data is not normally distributed. This can happen when the data is ordinal or rank-based. For example, this graph counts the impact of a drug on the health condition of the participants, and clearly the distribution is not normal. Here is another distribution which is not normal. In this case, the number of calls received per day follow a Poisson distribution. Likewise, the data may follow a geometric, binomial, or some other distribution. If data samples have many outliers, chances are the underlying distribution has heavy tails, so that outliers are overrepresented. Hence, the underlying distribution is not normal, because in a normal distribution, the outliers are generally unlikely. For example, consider this data that plots the number of days of hospital days, the number of days of stay in the hospital after surgery. 75% of the patients stay for up to 16 days, but a few patients stay well after. Hence, the data is not normally distributed. If you're not sure about what this figure plots, look up an earlier lecture on descriptive statistics to understand what is an interquartile range and how that links in with the outliers. The population can also be not normal if the data comes from an instrument that has limits of detection. For example, counting HIV viruses below a certain threshold may not be possible. Hence, sample values can be any of these values that you see on screen, or it could be not detected. So if substantial fraction of observations is not detected, the distribution is not normal because it appears like a part of it has been chopped off if we plot that distribution. So let us return to the problem. We cannot assume that the underlying population is normal. Our sample size is small, or perhaps we are not even comparing mean values as we were in the parametric testing. Instead, we compare median values of the sample. Then what do we do in all the above cases? If you're wondering why we may need a median, let's revisit the concept. We have so far based our statistical hypotheses on mean values. So the null hypothesis can be that the population's true mean equals some value mu naught, whereas the alternative hypotheses can be any of the three inequalities on screen. Now, mean accurately reflects the central tendency of a symmetric population where mean and median are identical, such as in this figure. So we know that another symmetric population with a different mean will be different from this population. However, in an asymmetric population, the mean and median are different, and the median actually better represents the central tendency. So we must consider the mean. As said earlier, median and mean are identical in a symmetric population, but in an asymmetric population, it is the median which divides the population into two halves. Also, defining mean in some situations may even be absurd. For example, in ordinal data, where each observation can be ranked but does not have an exact number attached to it, mean may not be defined. So what is the mean of these satisfaction scores, for example, on your screen? Their levels can be ordered, but we cannot assign a definite number to each level. If we do, these numbers will be arbitrary. For example, do we assign them scores on a 1 to 5 scale or a 10 to 50 scale? Each will produce a different mean. Although often such numbering is used, it is debatable in literature. Instead, median of ordinal data makes immediate sense. So you can order the sample data, as on your screen, and find the middle of this ordered data. And that turns out to be the value reasonable, as underlined. Hence, in this example on screen, the median value is reasonable because the amount of data on either side is equal. So let us devise a test for comparing medians. It is called the Signed test. Here the null hypothesis is that the true population median equals some value m naught, whereas the alternative hypothesis can be any inequality. Note here we are not assuming a small sample size, and the sample must contain independent but identically distributed observations. We cannot apply central limit theorem because that works with mean values or sum of random variables. Instead, we check how often the observed data is above or below the population median m naught. Obviously, if the data is distributed equally around the median, then this median is the true median of the population from which the data is coming. Hence, we compute the sign of deviation from the median. If a sample point is above the median, its sign is considered 1, otherwise its sign is 0. In the case of a tie, different approaches are used. Some researchers randomly assign the signs to all the ties, others simply omit the ties from the sample. In any case, we count the number of positive signs and denote it with capital S. Hence, capital S is the test statistic for the Signed test. So let's finalize the Signed test. As we said earlier, if the null hypothesis holds true, then the probability of seeing a 1 or a 0 must be the same, that is 1/2. So if we go back to our lecture on binomial distribution, when we compute the probabilities of counting different number of 1s or 0s, we use a binomial distribution. Hence we can say that capital S follows a binomial distribution where the size of the Bernoulli process equals capital N, which equals the sample size minus any omissions that we may have made to remove the ties. Now here's the big surprise. Note, we did not assume what the underlying distribution of the population was. However, regardless, the test statistic, capital S, follows a binomial distribution. Hence, it is a distribution-free test or a non-parametric test, as it does not require approximating the population's parameters such as variance that the t-test requires. Now for a large n, and when probability of success is high, we know that binomial distribution resembles a normal distribution. So we can rewrite it as a normal distribution here. Here the mean and the standard deviation of this normal distribution are the same as those of a binomial distribution. So the mean equals n times p, whereas the standard deviation is the square root of capital N times p times 1 minus p. As the figure shows, we have demonstrated this approximation as well. The code for drawing this plot is in the description of this video. Now, once we have a normal distribution, we can always standardize it and turn it into a Z distribution. The formula of standardization is on screen. Here, our random variable is capital S, and we substitute mean and standard deviation from 2 lines above on your slide to get the z-score for our observed S statistic. Thereafter, we can reject the null hypothesis if the z-score beats the critical values for a given significance level, or if the p-value is small enough. We can obviously conduct one-sided or two-sided tests, as we have done before for the z-test. So here is an example. Suppose the median number of days that patients survive after heart transplant is greater than or equal to 200. But a critic thinks that the actual median survival is less than 200. So this requires a one-sided test. And this is based on the data collected from 52 patients, where only 22 patients survived for longer than 200 days. Hence the S statistic equals 22. That is the number of data points that exceeded the median value of 200. So we conduct a signed test and compute the z-score by substituting all the values, and we get a z-score for minus 1.11. However, for a significance level of 0.05, the critical value is minus 1.645. In R, you can compute the critical value easily by calling the Q-norm function with the significance level of 0.05. Hence, the z-score is not low enough to reject the null hypothesis. Now, we had assumed the capital N to be large because then we could approximate the binomial distribution with a normal distribution. But if n is small, then this approximation doesn't work well. This is shown by the figure on your screens. In this case, it is better to use the binomial distribution directly. If you want to refresh your understanding of the binomial distribution, I put the link in the description below. The formula for computing the probability of S successes in a binomial distribution is on your screens. Now we want to compute whether the observed value of capital S and all values further extreme of it will fall within the critical region. For example, if we have observed S equals 8 positive signs in a sample of size n equals 10 after omitting ties, then we compute probabilities of finding 8 or more successes. That probability of finding 8, 9, or 10 successes and sum them all together. This is a one-tailed test, and we want to check if our median value is greater than the assumed median under null hypothesis. If the p-value, that is sum of probabilities as above, turns out to be below the significance level, then we reject the null hypothesis. In the case of a two-tailed test, we sum the probability of finding as extreme a value in either tail of the distribution and check if the sum of all the probabilities is still below the significance level. So here's an example. We must check if a drug reduces the repetitive behaviors in autistic children. Hence, the instances of repetitive behaviors before the drug use must be more than the differences after the drug use. Here the sample size is small, that is only 8 children. It is also paired data because we count the instances of repetitive behaviors before and after administering the drug to these children. So random variable xi's represent this count for each child. We obviously do not know if xi follow a normal distribution, so we cannot use a paired t-test. Also note that there are some large fluctuations in the difference column where 60 is an outlier, and this suggests a non-normal behavior. So we employ a signed test and we count how many times the differences are positive, and that equals 6. So the null hypothesis is that the drug makes no difference, so the median of these differences will be 0. The alternative hypothesis is that the drug actually does decrease the repetitive behaviors, and so the median difference must be positive. So a positive difference equals a success. Since we observed 6 successes, we conduct a one-tailed test and accumulate the probability of 6 or more successes using the binomial formula. And the p-value turns out to be more than 0.05, which was the significance level. Hence, despite 6 out of 8 successes, we fail to reject the null hypothesis. Note, you do not have to do these lengthy calculations in R. Instead, you can simply call the function binom.test and supply the appropriate parameters as on your screens. Note, hypothesis testing is not foolproof and can make erroneous decisions. For example, you may find it a surprise that despite having 6 out of 8 positive signs, we fail to reject the null hypothesis. A reason for that is that the sign test uses minimal information. It only considers the signs of the differences but ignores their magnitudes. Therefore, we may say that the sign test is limited in its power to reject the null hypothesis. It is a low power test and hence may produce an error in judgment. This is a good time to introduce you to the types of error in hypothesis testing. If we reject the null hypothesis when we should not, it is called a type 1 error. Whereas if we fail to reject when we should have rejected the null, then this is called a type 2 error. So we can say that the sign test may have committed a type 2 error. But again, we can't be sure. Another non-parametric test is called the Wilcoxon-Signed rank test. It is like the sign test, except that it also considers the magnitudes of differences. This works for paired or matched data. So the process to use the test is to compute the differences for each pair, omit the zero differences, then rank the magnitudes of differences, attach the sign of each difference to its rank. Then we conduct a 1 or 2 tail test on the median of differences. Here the test statistic is represented by capital T, and it is the minimum of the sum of positive and negative ranks. Alternatively, some texts use a W statistic, that is the sum of all ranks, but I leave that for self-study. And finally, we compute the test statistic with a critical value to decide. So let's consider the autism data again. Here we shall rank the magnitudes and then attach the signs to these ranks. So here are the observed differences. First, we order them according to their magnitudes and by ignoring their signs. Thereafter, we give the ranks. Here the smallest difference gets a rank of 1. Where the differences are equal in magnitude, they are assigned the average of the ranks that they are occupying. For example, in the second column, 10, -10, and 10 occupy the second, third, and fourth rank. And the average of 2, 3, and 4 is 3. Hence, all of them get assigned the same rank of 3. Finally, we attach the sign of differences to their ranks. So let us finish off our test. H0 says median difference equals 0. H1 says that median difference is greater than 0, hence the drug is effective. R plus is the sum of all positive ranks, that equals 32. Notice all the positive ranks are rather high. R minus is the sum of magnitudes of all negative ranks, and that equals 4. Notice the negative ranks are low in this example, and they're only 1 and 3. This should give you an intuition that even when there were negative differences, the magnitudes of these negative differences were rather small. So there is little evidence that the drug was working negatively and thereby increasing the repetitive autistic behavior. In fact, there is a greater evidence that the drug is working because that is why the sum of positive ranks is so much larger than the negative ranks. Therefore, T is the test statistic and takes the minimum of 2 sums, and that is 4. Finally, capital N is the number of pairs, that is 8. So here I show you the Wilcoxon-Signed ranks table that gives different critical values for each significance level. These values are given for the two-sided test, so the table instructs to double the significance levels for one-sided tests. I'll show you what that means with an example. Since n equals 8, we select the corresponding row in the table. Since significance level alpha equals 0.5 and it is a one-tailed test, we shall double the alpha to 0.10 and select the corresponding column. The intersection of the row and column gives the critical value, and that is 5. Our observed test statistic t was 4 and hence less than the critical value. Hence we reject the null hypothesis. You do not need to consult these tables though if you use a software like R that provides functions to do all that for you. Now here's something for you to ponder over. The signed test failed to reject the null hypothesis, but the signed ranks test succeeded in rejecting the null hypothesis. So clearly the extra information about the magnitudes of differences gave an advantage to the signed ranks test. Question is, if you have to choose between the two tests, what should you use? I suggest you research into it to build your own understanding, but I feel that the signed ranks test assumes that under the null hypothesis, not only the signs of differences are symmetric about the median, but also their magnitudes are symmetric around the median. This is a major assumption that requires deeper understanding of the population. For example, you must investigate how the repetitive behaviors fluctuate if we had given the children a placebo instead of a real drug. A placebo is not a drug, but in drug trials it is given to patients just to give them a psychological feeling of taking a drug. The psychological effect of taking some medication can improve the symptoms temporarily, and therefore the drug trials always compare the effect of a drug with that of a placebo. Hence, if the magnitudes of differences after giving a placebo are symmetric around the median, then that can indicate that we are good to use the signed rank test instead of the more conservative signed test. Now, signed ranks test works for the paired data, but we can also have unpaired data, as in a two-sample test. Now, we can use a parametric two-sample test if the samples come from a normal distribution or they are large. Otherwise, we must use a non-parametric test, and the one I shall introduce to you is called the Mann-Whitney-Wilcoxon test. As you can see, it goes by a few other names as well. Let us consider an example problem. Suppose we wish to test if a drug decreases the episodes of breathlessness in children. In other words, if it decreases the symptoms of asthma. We have 10 participants. We randomly divide them into groups of 5. We give one group the drug, and to the other group we administer a placebo. Clearly there is no pairing here, and the samples are completely independent. The placebo appears to have symptoms more often. Question is it statistically significant? If we plot the frequency of the symptoms as in the figure, the distribution is not normal and the sample sizes are small. Hence, we must use a non-parametric test like the Mann-Whitney-Wilcoxon test. Our null hypothesis is that both the populations are the same, and the alternative hypothesis is that they are not. So we pool the data together and order it from smallest to largest in separate columns. So 1, 2, 3, and 4 from the new drug appear in the lowest 4 places. Placebo also produces a value 4, so that is placed in the same row but in another column. This way we complete the ordering. Pause the video if you want to and verify it for yourself. Next, we rank the ordered data. Whenever there is a tie, we assign the ties an average rank as before. So the 2 4s here would have occupied 4th and 5th position. Hence they get an average rank of 4.5. Likewise, the 2 6s get an average rank of 7.5. Then again, we sum the ranks in 2 groups separately. Again, the test statistic is the minimum of 2 values, but these values are not merely sum of ranks in each category. Instead, U1 is the maximum value that sum of ranks can attain for one group, and from this maximum value, we subtract the actual sum of ranks for group 1. U2 computes the same for the other group. Some mathematical manipulation can help us deduct these formulas, as in these 2 steps. But this exact derivation is not so important as to understand the intuition behind this test. So you should think what happens if the two groups are completely different from each other. Suppose group 1 is consistently lower than group 2. Notice in this case, group 2 will occupy the highest set of ranks, and the sum of their ranks will equal R2 max. Hence, R2 max minus R2 should equal 0. Therefore, U2 equals 0. Similarly, group 1 will occupy the lowest set of ranks, and the sum of its ranks, R1, will equal R1 minimum. If that happens, then U1 simply equals N1 times N2. You can pause the video and verify this for yourself. In contrast, if the two groups are very similar, then the sum of their ranks will also be very similar. With that, I conclude this lecture, and I'll see you in the next one.